So we're into um, into chapter 2. And we're going to get a page up here so we can start working on these. Uh, also, Thursday's lab, I noticed, before we get started too far, I noticed Thursday's lab was on the web. Is lab number 4, and I skipped lab number 3. So I'm going to go back and I'm going to look at that just for a second, because I thought at one time we had lab number 3 in there, which is basically just a review of the so under courses 1020 syllabus, and we go down here and we look for there's lab number 2. So we do lab number 1, then lab number 2, and it's due, and then the next one is due is lab number 4. Does it even say we need to do lab number, let's say here's lab number 1, lab number 2, lab number 4, so we skip lab number 3. Lab number 3 is, let's go back and look at it. It's a lab on the oscilloscope itself. And I think what I did, now at one time I have actually had people go through and do this lab, okay? So this is the oscilloscope, and like I told you, this is not the one that we use. This is just a generic lab, but we use this one right here, which is the key site. So this is our oscilloscope, and it would pay you to look through this a little bit. Not that you're going to gain great insights from this, but I think that the more that you get affiliated with this wave, this specific model, it's a 2-channel model, which is one of the cheaper ones. This 2-channel model that we got. But the more that you get familiar with it, the better you're going to be able to do these labs. For a while, I will just help you hook up your lab in the laboratory and describe for you how to do it. And that's something you just have to get accustomed to, how to use the scope probe and the signal generator. So there are some methodology to that, and we'll talk more about that on Thursday, but I don't see any reason to do this as a lab. So I'm going to basically say, please look through this book at your leisure. Don't get really into it. It's a long book. It's 378 pages. Don't read it. Scan it and just look at what you need, and we'll talk more about it as we get into it. What is an oscilloscope? It's basically a time on the x-axis and then voltage on the y-axis, and that's what we have. And what you do now is you have to see time-varying signals. So you have to look at the oscilloscope in order to see the time-varying signals. To see phase shifts, you have to look at an oscilloscope to see phase shifts. And also different types of waveforms. You can see those basically all on an oscilloscope. It's a very powerful device, and you'll gradually become more and more familiar with it, and you'll get to like it. The ones that we have now have a magic button. I call it a magic button. It's a It's a scaling button, and you push that button, and it brings the picture to you from what you're looking at. You don't have to worry about scaling. You used to have to worry about scaling, and I was a good knob twister. I could, find it eventually, but that button I call it a magic button because it will find your waveform for you. So again, just look at this for a little bit. You don't have to peruse the whole thing. Just kind of have an idea that this book does exist, and we'll go through it. Also, we won't go through the book. It'll not be on any test, but it's for your reference, and it is there. So I have that. And then we will go to Lab 4 and I'll hand out Lab 4 on Thursday before we go to lab. Okay. Any questions anybody's got? So we will start the oscilloscope labs next 2 days from now, and you can use this book as a reference. It's a good book, but we don't have any testing over it. So it basically is just there for you and then I'll go through some of the initial, how you hook circuits up and that type of thing, and I'll review that before class. I'll review that in lecture on Thursday. I'll try to review that in lecture on Thursday. I'll try to be ready for you. How's that? So again, it's not a big deal, but it's a deal. Okay, so an oscilloscope, if you've never used one, did they use one at all in resistive circuits? Did you use an oscilloscope? No? A little bit, maybe? A little bit? Okay, so you do have a little bit of experience with it. I don't know. I haven't taught 1010 in so long, and I have not, I just don't know where you're at on that. But there are a few tricks. There are not many, but there are a few tricks, and some of those tricks we'll go over, some of them in class, some of them in the lab. So again, be prepared. It's just, honestly, I graduated from school and did not know how to use an oscilloscope. I was scared to death of them, and I had to use them in my work when I first got out of college and I started working in industry. And one night, I was so determined. I said, I got to be able to look things up with this thing. So I went and got one and went down, and I taught myself how to use an oscilloscope in one night at a factory. And I learned it, and from that point on, I was never afraid of them again. But up until then, I was kind of like, I don't like these things. But they were a little bit more difficult because, like I said, they didn't have the magic button. But they do now have a magic button, and we'll enjoy it. But also, it's a find the picture button. If the picture's over here someplace and you're over here, you hit that button and it brings it in, and it brings you what you're supposed to be looking at. And it scales it. Everybody follow that? It brings it down so you can actually see it. And that's a nice feature. And if you don't have that, sometimes it's kind of hard you get very frustrated. Anyway, so we're going to start on about 2.8, okay? Okay, so I think we worked through a few of these already, and I'm not sure. We will go back at the end of class. If you don't have your quiz, we'll go back and I'll do the answers to the quiz on Thursday, quiz 2. Okay, hand them in today, but at the end of class. All right, so in the circuit 2.25, if the input is 100 hertz, what is the value of the inductor in millihenries? Okay, so in number 8, up until number 8, they're pretty straightforward, and we went through several of these. But number 8, it does it backwards. So for number 8, the x sub c x sub L, rather, is equal to 2 pi FL. Now, we know there's also a J in front of it, but we can ignore the J for this point. Okay, so we can ignore the J. So now we go back and we look at it and see so this is equal to minus J 500. So you can just basically say 500, okay? You could drop the minus J. You can say J is equal to, you can say minus J is equal to, I said 550. Minus J is equal to minus J, but you can drop out the minus J. So 2 pi FL is equal to 550, all right? So what is L? It's just a backwards calculation, isn't it? It's, oh, and frequency is at 100, so they give you that. So they give you F is equal to 100. So L is equal to 550 over 2 pi times 100, right? So what is L? 0.2387. Any questions about that? That's all that is. It's just backwards calculations, and you can drop the J's. Okay? Yes, sir. Isn't that, isn't it, oh, I'm sorry, it's the 150. It's the one, I'm looking at the wrong one, yeah. Sorry about that. It's 150. Takes me a while to get going on these. Okay, so it's 150. And then in the circuit, again, number 9, if the input frequency is 200 hertz, what is the value of the capacitor in microfarads? So basically the same thing. 2.9 is X sub C is minus J over 2 pi FC. So F, they give you, again, is equal to 200. And then they ask you what the value of C is if this is minus 150. There's your minus 550 is equal to minus J over 2 pi times 200 times C. And this is, there's a minus J in front of this. So the minus J's go away. So 550 times 2 pi times 200 is equal to C. And let me get this right. So X sub C is 550. So, okay, so this C goes over here, and everything else goes, got that backwards. I'll get it. C is equal to 1 over 2 pi times 200 times 550, or 1.44 times 10 to the minus 6, or microfarads. That's 9. Okay, so basically all this is asking you to do is to work through that formula. Okay, that's number 8 and number 9. Number 10. Draw the voltage and current waveforms for the circuit in figure 226. Okay, so here is a circuit with this equation for your voltage. Draw the waveforms. So that's that one. Okay, so let's do that. All right, so we have 2-10 is a graph. So what is the peak? Well, it's a sine wave, so it cuts through at 0, and the peak is, for voltage, is at 12. Okay? The negative's at minus 12. Now, what else can we ask for here? So what is this? This is, frequency is 1 over the period. And what is the period? Well, the frequency is 2 pi f, so f is equal to 100. So this would be 1 over 100. T is equal to 1 over 100, or 10 milliseconds. So the period from here to here is 10 milliseconds. Any questions about that? 11, same thing. That's the voltage, and what would be the current? They asked for the current as well. Well, the current would be that divided by 100. So basically, it's the same circuit, it's the same exact picture, except it's 12 divided by 100, which would be what? 120 milliamps. So it would be the same circuit, but the peak would be at 120 milliamps. That's number 10. Number 11. Draw the voltage and waveform for the circuit here. The current is 1e minus 3, or 1 milliamp times 1000 t. So this would be 11 would be the same thing, sine wave F is 1000, t is 1 over 1000, or 1 millisecond. So from here to here is 1 millisecond. Okay, and the value of that is what? What is the value of the voltage through the 100 ohm through the 100 ohm resistor? It's this value 1 milliamp times 100 ohms, or 0.1 volt. So it's either 1 milliamp or it's 0.1 volt is the peak. Minus peak would be minus 0.1 volt. All right, and now they get more interesting, because this is number 12 is what? It's a capacitor, isn't it? All right, so now we get a capacitor and we get a voltage. So now we have a 1 volt peak sine with a frequency of 10 kilohertz and C of 3.3 nanofarads. Okay, so now let's look and see what the voltage looks like through the capacitor and the current through the capacitor. Okay, so let's just ask that question. All right, so what is in 12? So here is our sine wave. Okay, so with 12, everybody follow this, 2.12. So we have a circuit of 1 volt peak, frequency of 10 kHz, and a value of C is equal to 3.3 nanofarads. Nano means -9. So what is the X sub C? X sub C is equal to what? Minus J over 2 pi FC. So X sub C is what? Minus J over 2 pi times 10 to the 4th times 3.3 times 10 to the minus 9th. Let's calculate that out and see what we got. Okay, so you don't need complex mode for this. 1 divided by parenthesis 2 times pi times 10 to the 4th times 3.3 and take on. So what did you get for that? Anybody get the answer for that? 4.823. times what? Ten to the third, it's 4.823 times 10 to the third, right? And there's a minus j in front of it. Okay, so now this time we have to use the minus j. All right, so V across this capacitor is equal to what? V across this capacitor is equal to 10, excuse me, it's equal to 1 volt. It's 1 sine 2 pi times 1,000 times 10,000, 10 to the fourth, times T. All right, that's my voltage. Voltage across the capacitor is equal to that. Why is that? Because if it's voltage here, it's got to be voltage here. It's got to be the same voltage here as the voltage here. So if the voltage across this is equal to that, the voltage across here is equal to that. Now, what is the current? I sub C. Well, it's equal to V, which is 1. You just take the 1, forget about all this other stuff, divided by X sub C, which is what? 1 divided by minus J 4.823 times 10 to the third, okay? Now, the minus J becomes a plus J in the numerator. So what does this equal? Well, you forget about the J for a minute and you get the value of the magnitude, which is 0.207 milliamps. But now, if you put this in your calculator and you crank it out, you say, in the complex mode, okay, now you go to the complex mode and you hit enter, and you say 1I divided by 4.823 is equal to what? And do that in polar. I want the answer in polar. Okay. It's 0.207 at angle 90. So if this was at angle 0, this was at angle 0, okay? Theta here is equal to 0. Theta here is equal to 90. So if you were to write the equation for the current, you'd say I sub C equals what? 0.207 sine of 2 pi times 10 to the fourth T plus 90 degrees. Everybody follow that? And if you remember, ICE, current leads voltage in a capacitor. So who's ahead, the plus 90 or the 0? Plus 90. Here's your circle. Here's your phasor diagram. Here's this voltage at 0. Here's this current at 90. So who's ahead? Who's ahead in the dog race? The voltage, this is my voltage, or this is my current. Current's ahead, okay? Because you're going in this direction. You're going around this way. Everybody follow that? Current is ahead by 90 degrees, and that's what's reflected here in this equation. If you look at it on an oscilloscope, what do you see? You see the sine wave for voltage, and you see, this is my voltage, and you see what is sine of something plus 90 degrees. When you move ahead 90 degrees, here's my sine wave, but I move ahead 90 degrees. What is this? So basically, it's this circuit moved like this. It's like this. What is that? That's the cosine wave. So what I did was I made it a cosine waveform, or I said sine plus 90, which is equal to cosine. So if you look at this on an oscilloscope, what do you see? A pure capacitor. You see voltage and you see current 90 degrees out of phase with each other. All right? So this is a dog race. And one is ahead of the other by a quarter of the way around. So a quarter of a lap. Okay? What do you think it is with an inductor? Just the opposite, right? Eli, E-L-I. Who's ahead in an inductive circuit? Voltage is ahead of current in an inductive circuit. So you will see the phase shift, but the other way. All right? Here's voltage ahead of current. Here's current ahead of voltage with a capacitor. With a capacitor in an inductor, it's the exact opposite. Okay. All right. Now this is the other guy, the other brother. Okay, 13. So okay, so you got an I. Excuse me. Here you've got a voltage. Okay, so number 13, same song, second verse. Number 13, you've got a supply, and it's got a 2-volt peak to peak. Now this is where they get you, because it's, what is a 2-volt peak to peak? It's 1-volt peak, right? Exactly. So it's the same thing as the other one, but they basically it's playing a game with you, okay? But it's 40 hertz and L is 33. So voltage and current for this guy. So let's do this and see what we get, okay? All right, so this is my sine wave for my voltage. Voltage is equal to 1, Ted. 1 sine 2 pi f, which is what? In this case, it is 40 times t, 2 times ft. That's my voltage, and that's, you just label as V peak, or you don't have to label as V peak because it's understood when you write this is peak. It's understood. All right? So that's the peak value. That's the peak that it goes to. Now, what do you do for current? I equals what? Well, you have to find the impedance. And this is 33 millihenries. You have to find the X sub L. What is X sub L for the circuit? J 2 pi FL. So it's equal to J times 2 pi times 40 times 0.033. What is that? X sub L. 2 pi. 2 times pi times 40 times 0.033 equals, having troubles today. My eyes are not focusing good. 2 times pi, Ted. 2 times pi times 40 times 0.033 equals, okay, 66 over 25 pi. Option equal, excuse me. I got to go back. Okay, 2 times pi times 40 times 0.033 equals 66 over 25 pi. Shift equals 8.2938. Okay, so it's equal to J 8.2938. That what everybody got? All right, can you do this on a test? I don't know. Well, we'll see. I can't even do it on a test. I can't see today. Anyway, but that's beside the point. Okay, so now that is my V, or that is my, there's my V. What is my I? It's 1 sine, or it is basically, you just say the word 1 because that's all it is, okay? It's, you can forget about the sign. Just take the peak value okay? It's 1 divided by J 8.2938. So what is that? Minus J in the numerator, right? Over 8.2938, which is equal to what? 1 divided by 8.2938, or you can say minus I if you want to. Now let's just do that. Okay, so it's a minus, use the minus sign up above, don't use the subtract button, use the minus sign up above, minus 1I divided by 8.2938 equals minus 5,000 over 41,469I. Okay, so let's just do option down 1 equals shift equals. So that is equal to 0.1205 at minus 90 degrees. Now, this is what you write in for the magnitude. You add this to the, so it's I is equal to 0.1205. Now you bring your sign 2 pi times f times 40 t, and then you bring the minus 90 degrees, and you put parenthesis, you put parenthesis around this. Now with this case, the voltage is the sine wave, and the current is like this. It's lagging by 90 degrees. So basically it is doing this. So this is my voltage, this is my current, and my current is lagging by 90 degrees. If you had a pure inductor, you would see this 90-degree shift. Eli, voltage is ahead of current in an inductor, all right? You see this shift. And you say, now, tell me another one. Tell me all this other stuff. But this is exactly why we study this course, is because these things don't look like, who would ever come up with all this stuff? Because they work. This is not something that somebody just invented out of thin air. They found that this is how to explain real physical phenomenon. In other words, if you have an inductor and you have an AC waveform, this is exactly what happens. So this is not something that you can just say, this is not reality. It's reality. It's exactly how to explain this J number, this J operator explains how this thing actually works. Now, in fact, you never have a truly pure inductor or capacitor. You always have some resistance. You always have some. It's never just exactly. So you'll see this kind of thing. Anyway, now this is voltage, and they do the same thing for current. So he plays the game both with voltage and with current. All right? So what do you think happens with current through a capacitor? If current is, all right, I'm not gonna do this one for you. I'm just gonna ask you, what would you think that the equation for current would look like if you had a pictorial of if you had number 14, okay, excuse me, number 14, if you had this picture in your mind, here's a current supply, okay, here's a current supply, and here's a capacitor, all right? And ice. So here's my picture of current, okay, sine wave. Nice, pretty sine wave, right? Like that. Now, what would be the picture of voltage? It would cut back here, and it would be up here. So basically, what would it be? This is my picture of current. This is my picture of voltage. So what would be my equation for voltage? Voltage is equal to blah, 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 sine of 2 pi f t plus 90. So here, the voltage is ahead, So, no, voltage, I'm sorry, got it wrong. Ted, voltage is behind in a capacitive circuit, so it would be minus 90. And it would be, instead of being ahead, it would be behind. So this picture is backwards. Sorry about that. We'll get there. Here's my current vector. Here's my voltage vector. So it would be minus 90. It would be back here. So if you're spinning this way, this guy is lagging by 90 degrees. So here's my current. And here would be my voltage. It would be cutting right here. So it would be, this would be my voltage. It would be like that. So here's my I, and here's my V. So it would be 2 pi ft minus 90. I had a hard time. I don't know if it's just me or whatever, but it's a... Okay, so it's sine of 2 pi ft minus 90, and here's my I and here's my V for this problem. Because now we discussed I, this is I, so I gets the sine wave, right? I gets the sine wave, and then C is this guy right here, so V is lagging by 90 degrees. So you can get your magnitude, but you're lagging by 90 degrees. Okay, now, let's see if I can get this one. Here is I through an L. This is the opposite. This is the one I was trying to do just a few seconds ago. So this is 15 is, okay. Now, here's my L, and here's my I is equal to blah, blah, blah. Sine, it's equal to what? It's a 2 amp, okay, peak to peak, so it's 1 amp sine. So I is equal to 1 amp sine of 2 pi times F times 40 times T. There's no plus zero, it's just say, you just say 2 pi times F times T. Now, what will be the voltage? It'll be some number times what? Sine of 2 pi times 40 times T. This is an L. Eli, right? Plus 90. The last one was minus 90, but now you say plus 90 because voltage leads current by 90 degrees in a pure inductor. So, if the inductor starts with the I, you add 90 for the V. If you start with a V, you subtract for the I. Okay? That makes sense? That's exactly how it's done. All right, enough on that. I think we beat that pretty bad. Sorry. All right, so let's go down and do some more of these. Let's go down to number 24. So here, find the current in a circuit. So number 24 is one where you have to... Now, what we did right there was theoretical. You'll never have it in the real world. Here's something you'll have in the real world. So number 24 is a... Now he draws it backwards. I always draw it with the voltage on the left. He draws it backwards. I don't really care. Doesn't matter. All right. So it's 1 volt peak over here. I'm just going to write the 1 volt peak. I'm not going to write all this other stuff. 2K up here. 3 microfarads over here. Okay. Now what must you do before you can find I in the circuit? You must find X sub C, right? What is X sub C? Somebody tell me. I always like Ferris Bueller's Day Off. I watch it with my kids again and again and again. And I like that guy, that teacher said, anyone, anyone, anyone? I've done that over the years just to mock the guy. But does anybody have any idea how to write X sub C? What's X sub C? Everybody should know this by now. What is X sub C? Minus J over 2 pi FC. Everybody ought to have that in their back pocket, written on their shoe or memorized, or in that one piece of paper that you have that you can carry with you and you should know. You should memorize this. Minus j over 2 pi fc. Okay? So what is x sub c? You've got f. What is f? 50, right? F is equal to 50. You pull it out of the equation for the sine wave. Okay? 2 pi f times t. So what would be x sub c? X sub c is equal to what? Who can get it first? Minus j over 2 pi times 50 times 3 times 10 and minus 6. What would that be? What is it? Okay, it's 1 divided by 2 times pi times 50 times 3. Okay, take on it. I tell you, this is a terrible day. 1 divided by parenthesis 2 times pi times 50 times 3 parenthesis again. Okay, so it's 10,471, right? Minus j times 10,471. Is that right? 2 times pi times 50 times 3. Oops, no. 1 divided by. I can't get. Somehow my brain is not working today, so you have to help me. 2 times pi times 50 times 3 in parentheses equals. Nope, it's not that. It's 1,061, right? 0.061 k ohms. Okay, so there's my my x sub c. So what is I? If this was an R and this was an R, what would it be? I is equal to V1 divided by the sum total of the R total, right? R total now is what? Instead of R total, it's Z total, okay? What is Z total? It's equal to 2K minus J 1.061K, all right? Now you have to go put this in the denominator, 2K minus J 1.061K. Equal what? In polar. What is it? You must be in complex mode, all right? So you got to get it over into the second. Everybody see the second picture? Everybody see that? You got to get it in that mode. If you don't have this calculator, please get one like it in that range, something that can do this. Okay, so now you get into the complex mode. Equals, so complex mode equals 1 divided by parenthesis 2,000 minus 1,061 I in parenthesis equals what? Blah, 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 something, option down 1 equals shift equals, so I get what? What is my current equal? 0.441 milliamps at angle 27.9 degrees. Okay. Make sure you can do this. Please don't just say, I'll get it tomorrow or I'll get it one of these days. Get this now, okay? Once you get it, you're locked in for the rest of the course. If you don't get this, first test not going to be good. the rest of this course isn't going to be good. So please get this. Everybody got that? I could go around and look at everybody's, calculator and see if you got it or not. I'm not going to do that. But on the other hand, I want you to understand that you have to be able to do this in order to get through this course, right? You got to be able to find this using the techniques in the calculator. You beat it right down right away. Any questions about that? Okay. Well, that's the kind of question you're going to get on a test in spades. A lot of them. You're going to get a lot of these kind of questions, and that's what you've got to be able to do. Okay. Okay. Now, number 20. What? I did number 28 next. Is that? I don't remember which ones I did. I'm just working through some of these, so I'm not doing them all, but I'm doing enough of them that you can get the idea. Okay, so number 28. The circuit of figure 235 determine the circulating current and the voltage across each component. So this is the same song, second verse. Okay, so this one, now what did they do though differently? Which I promised you I would do for the most part in most of the applications that we do. What's the difference here between 24 and 28? What do I do now? What did he do now? He skipped the phase where he actually makes you calculate the x sub L, right? He skips that phase. Why does he do that? Because on a test, if you miss that, you mess up everything. So step one is to find the x sub L. So right now, the most important thing is finding the I. And if you don't know how to find the I, or it says determine the circulating current and the voltage across each component, well, basically now you have to find the I and then multiply that times this to get the voltage here and multiply that by this to get the voltage here. So he's forcing you to do in that order, but he's giving you this. If you miss this, everything else goes to pot. Everybody follow that? If you don't get this value, you're had. So he's giving it to you. And I'll do that for the most part. I may ask you one, like number 24, but number 28 is the classic way we do these questions because we don't want you missing the first step and then having to argue with us about, I don't want a line of people halfway down this row saying, I got it all except the first thing, the x sub L. It's hard to go back and undo whatever. It's hard to go back and undo those kind of questions. So we basically, for the most part, give you the x sub L or the x sub C. We give it to you. So what would be the answer here? Now, is this peak or RMS? Or I don't care. It's usually RMS, okay? Unless they tell you V peak, it's an RMS, but we don't really care. Now, if they ask you for the power, then we do, but they didn't ask you for the power. Does everybody follow that? If this was a power question, then you would have to say that has to be RMS. I assume 2 volts RMS, because that's how you calculate power. But if it doesn't, this is so confusing to most people. Say, which is it? Is it peak or is it RMS? I don't care. You work it with the two and you go, okay? Some people might say, well, that's really peak. Some people might say, well, that's really RMS. He says in the book, unless it's labeled, it's RMS. So basically you assume RMS. But some people don't. Some people write that and they're assuming peak. Please don't get upset about it one way or the other. Was this peak or RMS? Don't throw the square root of 2 around unless you're absolutely asked to, okay? So if you have to convert from one to the other, then you use the square root of 2, but otherwise, leave it alone. Just use the 2 like it's a DC circuit and go for it, okay? That's all this is about. Do not get hung up on, is this peak or RMS? Who says I don't care? There's a guy on TV who used to say that. But we don't care. What was, forget his name. Anyway, we don't care. We go on. Somebody tell me how to set this circuit up. How would you solve this circuit? Anyone? Anyone? Say again? Yeah, you got to. What would be the total impedance of this circuit? What would be the total impedance of this circuit right here? 500 plus J 40. Does everybody follow that? What would be I? It's this divided by this plus this, yeah. Okay? Everybody see that? That's all it is. This is just like resistive circuits, except now you've got a J in front of something. And you got to use a stupid calculator, okay? And that's it. That's all this is. Not a stupid calculator. It's the calculator that you need, and that's because of these circuits. And this looks strange, and this looks like, what is it going to tell us next? Well, this is basically it. The people that discovered this stuff, because this is not, this is back in the 1890s, 1880s when this guy discovered all this stuff. He was a brilliant guy, but he actually found that this way of solving these questions actually show how AC circuits can be calculated. And it's brilliant. The guy's name is Heaviside, British mathematician, Heaviside. But anyway, he found this. He found how all this stuff works, and he wrote this stuff all down. And I guess he's Scottish, English, Scottish, whatever. Probably talk with a real good brogue or something like that. Probably if he came in here today, we would hear him say, yeah, nice guy, whatever. But he was brilliant. But anyway, he found all this stuff and actually works in the real world. And it explains how AC circuits, you can calculate currents and voltages in AC circuits, okay? So what have we done? For all linear circuits, capacitors, inductors, and reactors, we have found a way of finding voltages and currents in AC circuits. And that's a big deal because most of the circuits in electricity are AC circuits, because we can now go back and we can calculate them. It's a nice way of putting that stuff, kind of a way of doing it. So let's do this one, and we'll get through this, okay? Anybody got this already solved? So what would be, what was I for number 28? It's 2 over 500 plus J 400. Now the calculator part, right? So hit menu equals, get it into the complex mode. It's always got to be in the complex mode before you do this, and say 2 divided by parenthesis 500 plus 400 I in parenthesis equals. Option down 1 equals. So then you do the option, and then the down, the down 1, and then the equals. And then it gives you a number. And it gives this number straight out. You don't have to hit, sometimes you have to hit shift equals as well. But right now we've got it as what? 3.123, an angle minus 38.66 milliamps. So we've got our current, right? Everybody agree with that? Now, what is our voltage across the 500? V of the resistor is equal to what? 500 times that. What is our voltage across the L? It's J400, very good, times that, okay? So what is our VR? 3.123. Now you can use your angle, so it's 3.123, shift engineering, and that gives you your angle minus 38.66 times 500 equals 1.219. Oops, no, sorry. Shift equals. It's 1.219. Oh, nope. Option down 1 equals shift equals 1.561 angle minus 38.66. So that's our voltage. That's our voltage across our resistor. What is our voltage across our inductor? It's I. It's 400I. You got to put the 400 first. 400I times 3.123 milliamps at angle minus 38.66 equals option down 1 equals down equals 1.249 at angle 51.34 degrees. Okay. Notice the difference between here and here is what? 90 degrees. It doesn't always work that way, but it does here, okay? So the inductive voltage leads the resistive voltage by 90 degrees. All right? Any questions about that? Yes, sir.
If we wanted to, just put the voltage divider formula also work in this scenario?
It sure would, but there's no need because he made you do current. Yeah, you can use voltage divider and it works, but he asked you to do current first, so he pegged you. You can't do just voltage divider. But if he only asked for voltage, just use voltage divider and you're done. Yeah. By the way, voltage divider is a one-step snake. Anybody know what a one-step snake is? What's when you find current and then you have to find voltage, that's a two-step snake because you have to find voltage, we have to find current and then find voltage. That's 2 steps. If you just do voltage divider, it's a one-step snake. Does anybody know what a one-step snake is? It's a snake that if it bites you, you only have 1 step before you die. Okay? I call it a one-step snake. It's not really, but it's 1 step. You only have to do one thing and you're done. Voltage divider is your best friend because you can use it for all kinds of things. And it's a 1 step, done. Okay? Voltage divider is useful for a lot of stuff. And if you don't think it is, it is. If you want to step down from a higher voltage to a lower voltage, it's one of the things you build a voltage divider. Voltage divider, 2 resistors. Make sure they're high enough so that what you're trying to step doesn't affect it. You'll figure it out. It's just you use it again and again and again. It's useful, very useful. So anyway, so that's number 28. Any questions so far? Hopefully you're having some fun. I know this is not, believe me, I know this is not the most fun in the world. I found the best defensive mechanism for this, okay? I hated this when I took this stuff because you sit there. I should bring the slide rule in someday. I'd sit there and show you how, what we had to do. And you say, well, that sounds like, you had to walk to school three miles uphill to go to school in the snow, and then you had to walk home 3 miles uphill in the snow. Yeah, that sounds like that kind of a complaint. But the difference between that and this is phenomenal. And you say, well, I could just buy a $200 programmable calculator, knock everything in the head, I don't have to even worry about that. But the only reason you're ever going to do any of this stuff, not really, you're going to do a little bit of this stuff, calculating motors and stuff like that and other things. But the real reason you're doing this is because if you ever settle down and actually do get a job where you do really need a PE test, to take the PE test, this is your best friend because it will knock those problems in the head. And this is the kind of problems you'll see on your fundamentals test, and then your PE test was, I'll explain one of the problems that was on my PE test, and I camped on them. I mean, I literally just settled in on those problems because they were like this, but worse, okay? But because I didn't have a calculator like that at that time, I was severely strapped. But with this calculator, you can blitz through problems that are really, really hard without much difficulty. And this is allowed, this type of calculator is allowed on that test. So if you ever do want to get a PE, this, and know how to do these, and you'll have a PE behind your name. I can't guarantee it, but you'll more likely than not have a PE behind your name, okay? These are the kind of problems they camp on. So I don't like them. I don't think most of the time that they really amount to that much. Although sometimes you do have to worry about lead and lag and all that kind of stuff. Um, it does happen. You do have things that, that do, you do have problems that are accounted for by lead and lag circuits, okay? So anyway, I think the dog, my mind latches onto something that's going around in a circle, and a dog track is exactly what it is. I mean, it's like, and there's a lead and there's a lag dog. And if you can't see that, you have to find another way of thinking about it. But it's exactly how this stuff works, okay? It's hard to explain, but the dog track approach, in my opinion, as dumb as it sounds, is a good way of looking at it. Okay, so you say, you tell your relative or whoever that this guy talks about a dog track in my electrical class, and you said, well, we never had that in our electrical class. And I'm just saying, yeah, but it explains why this stuff looks this way, and it looks like a dog track to me. So again, I'm just trying to help you from my vantage point, which is I struggle with this stuff too. Okay? I didn't get an A in the course, by the way. When I took this course, I got a B. All right? I struggled. I took it, and the guy, I still remember the teacher's name, Tim Trick. Timothy N. Trick. TNT. Anyway, he was a good Ohio State alum. Never really cared for Ohio State alums, but anyway, that was one of them. But he was in Ohio State. He graduated from Ohio State with a PhD in electrical engineering. Anyway, he was one of my teachers. Whoop de who, huh? So now we're down to this, which is what? Same song, second verse, except this now is a current supply. So what would be determine the voltages across each component here? Now, with this one, you've got current as your driver, right? It's 5 milliamps. And I'm going to ask you again, is this peak or RMS? Probably RMS, right? Now, here is this guy up here, it's 2.2K, and over here it's J100, all right? Now, what is I through that circuit? 5 milliamps. Why? It's guaranteed, right? Why is it guaranteed? Because it said so over here. So what is the voltage across here? I don't care. It's whatever the voltage is to guarantee that this thing works. See, well, if I change the frequency, is it going to stay the same? Yes, it's going to stay the same because it's guaranteed. This is the current right through the whole circuit. So what's the voltage across the 2.2K? Well, it's 2.2K times 5 milliamps, exactly the same as it was before. What is the voltage across the L? J100 times 5 milliamps, okay? So what does that do? It's 5 milliamps times 100 at angle 90, okay? The J is equal to angle 90 minus J is equal to minus 90, all right? So I can just write it. I don't have to do anything else to do that. Everybody follow that? Knock that one in the head. It's easy. Now, what is the applied voltage? Now you have to do something. Now you have to actually do something here. So voltage source is equal to the voltage across this thing, which is equal to what? It's this plus this. 2.2K times 0.005 plus 100 times 0.005 at angle 90. Now, can you find that in your calculator? Yes, you can. One step. This is a one-step snake. So try that one. 2200. Okay, so mode setup, complex. All right, anybody have any problem with that? So now you've got, that's a 2200, 2200, Ted, times 0.005 plus 100 times 0.005 I. Or I could say at angle 90. Okay? Everybody know how to get the angle? It's shift and the I. Everybody follow that? Shift and the I, it gives you the angle, and you put the 90 in. Okay, so that's that. Now you said equal, and it's 11 plus I over 2, option down 1 equals. Square and shift, it's 11.011 at angle 2.603 degrees. Okay, so it's equal to what? 11.011 at angle 2.6 degrees. Everybody get that? See how that's done? Pretty straightforward, isn't it? Yeah. You can do that with this calculator very, very quickly. Any questions, any comments? Help. You got it, right? Any questions anybody's got? Okay, so I want your quiz. I think I'm done. Well, even though I didn't work number 33. Anybody have any questions? Okay, so I want your quiz. Hand it in. I'll see you on Thursday. I think there's one person that needs to go to the lab today. And then, okay, so we'll take you to the lab and get you started. If anybody else needs to go over anything in the lab, I'm going up there. I'm going to open it for him and get him started. And that's as far as I'm going to go with that. But if anybody needs to go to the lab today, for any reason, I'm going up there for just a few minutes. Hand your quiz in. We'll see you on Thursday. I'm going to shut this off. You can hand it right there. Thank you.
This Thursday?
Okay, thanks. It's okay. Thank you. You could turn in your labs too. Yes, please do. Yes, please turn in your lab. Yes.